Most people think they know what the Big Bang was. They picture an explosion, a gigantic blast, a point in empty space that suddenly went boom, throwing galaxies outward like cosmic shrapnel. It's a powerful image. It's also wrong, not slightly wrong, wrong in a way that quietly distorts how we imagine everything else. So let's start with a very simple question. What does it actually mean to say the universe began? Because right now, as you're sitting here listening, the universe is still doing the same thing it was doing back then. It's expanding, not away from you, not from a center, but through you. And that single idea changes everything. Here's the first thing to unlearn. The Big Bang was not something that happened inside space. There was no empty room, no surrounding darkness, no outside into which the universe exploded. Space itself is the thing that changed. Imagine for a moment that distance is not fixed, that the rulers we use to measure space are quietly stretching everywhere all at once. If every ruler stretches together, nothing looks like it's moving until you compare now with then. That comparison is what astronomers do. They don't watch galaxies fly away. They watch light get stretched. Light is the universe's memory. When a distant galaxy sends out light, that light travels for millions, sometimes billions of years before reaching us. And during that journey, space keeps expanding, so the light wave gets stretched with it. Longer wavelength, lower energy, redder color. This is called redshift. But don't let the name fool you. Redshift isn't telling us how fast galaxies are moving through space. It's telling us that space itself has grown while the light was on its way. The farther the light traveled, the more space had time to stretch. That's why distance and redshift are connected. Not because everything is running away from a point, but because the universe is getting bigger everywhere. Now pause and think about the implication. If you rewind this process, not objects moving inward, but space itself shrinking, the universe becomes denser, hotter, more compressed. Keep going back far enough, and you reach a state where everything we can see today was packed incredibly close together. That state is what we call the Big Bang. Notice the phrasing, a state. Not necessarily a moment of creation, not the birth of everything from nothing, just the earliest phase our current physics can describe. And that distinction matters, because the equations don't say this is where the universe popped into existence. They say this is where our understanding stops working. This is the part that often gets missed. The Big Bang is not a claim about ultimate origins. It's a boundary, like asking what's north of the North Pole. You don't find more land. You find the limit of the map. So when cosmologists talk about the beginning, they're not talking about the beginning of everything. They're talking about the beginning of what we can reliably calculate. And that means something profound. The Big Bang was not the start of space expanding. Space was already capable of changing. The Big Bang was the moment the universe became hot, dense, and visible. And here's where things start to get really interesting. Because if the Big Bang wasn't the absolute beginning, what came before? That question is not philosophy. It's physics. And answering it requires us to think about how space, time, energy, and even causality behave when pushed to their limits. But before we go there, we need to understand one thing clearly. The universe is not something that happened once. It is something that is still happening, and you are not watching it from the outside. You are inside the expansion itself. If the universe is expanding through you, the next question is unavoidable. Expanding from where? Every explosion you've ever seen has a center, a firework, a bomb, a ripple in water. There's always a place you can point to and say, that's where it started. So where is the center of the universe? Here's the strange answer. There isn't one. Not hidden, not far away, not waiting to be discovered. It simply doesn't exist. To understand why, we have to stop thinking of space as a container. Space is not a box that things sit inside. Space is more like a relationship, a way of measuring distance between things. And that distance can change. Imagine you draw a grid on a rubber sheet. Straight lines, perfect squares. Now stretch the sheet. The grid stretches with it. Every square grows. Every distance increases. But here's the key point. No square becomes the center. Every point sees every other point moving away. If you were standing on one square, you'd swear you were at the center. But someone standing somewhere else would say the same thing. And both of you would be right. That's how cosmic expansion works. Galaxies are not racing through space like bullets. They are mostly staying put. What's changing is the space between them. The universe is not expanding into anything. It's expanding by creating more distance between everything already inside it. This is why every observer in every galaxy sees the same thing. Distant galaxies moving away, farther ones moving away faster, not because they're special, but because expansion looks the same from every location. This idea is deeply unsettling. It means the universe has no preferred place, no center, no edge, no special viewpoint, not even ours. And that tells us something profound. The laws of physics do not care where you are. The universe is built so that no position is fundamentally different from any other. That symmetry is not philosophical. It's mathematical. This brings us to a man who rewrote gravity itself, Einstein. Before Einstein, gravity was a force, a mysterious pull between objects. After Einstein, gravity became geometry. Matter and energy don't pull on space. They shape it. Space and time form a flexible fabric, what we call space-time. And that fabric can stretch, curve, evolve. When Einstein wrote down the equations describing this fabric, he found something unexpected. A universe filled with matter cannot remain perfectly still. It must either expand or contract. A static universe is unstable, like a pencil balanced on its tip. At first, Einstein didn't like this. He wanted an eternal, unchanging cosmos. So he added an extra term to his equations, a mathematical fix designed to hold the universe still. Later, when observations showed the universe was expanding, he reportedly called that fix his greatest mistake. Not because the math was sloppy, but because the universe refused to sit still. What's remarkable is this. The expansion of the universe is not something imposed from outside. It falls naturally out of the structure of space-time itself. Once you allow space to be dynamic, change becomes inevitable. Expansion isn't an event, it's a behavior. And it didn't just happen once, it's still happening now. Between every pair of distant galaxies, space is quietly growing. Not dramatically, not explosively, but relentlessly. This is why the Big Bang does not describe a point in space. It describes a condition of space-time. Everywhere was once closer together. Everywhere was once hotter. Everywhere was once denser. There is no place you can travel to and say, here is where it all began. The beginning, if we can call it that, was everywhere at once. And now, something subtle but crucial. If space is expanding, and if energy and matter shape space-time, then the early universe wasn't just small. It was governed by physics under extreme conditions. Temperatures so high that atoms couldn't exist. Density so great that familiar forms of matter broke apart. The universe was not yet structured. No stars, no galaxies, no planets, just energy, particles, and motion. And yet, somehow, from that simplicity, everything complex eventually emerged. If you want to know what the early universe was like, you don't dig. You don't travel. You wait, because the universe doesn't hide its past. It sends it to you at the speed of light. Light is strange. It has no memory of time passing. From the light's point of view, it is emitted and it arrives instantly. But for us, light is a messenger, a traveler carrying information across enormous distances. When you look at the sun, you see it as it was 8 minutes ago. When you look at a nearby star, you see it as it was years ago. When you look at a distant galaxy, you see it as it was millions, sometimes billions of years ago. So every telescope is a time machine, not because it moves through time, but because it collects ancient light. Now imagine pushing this idea as far as it can go. What happens if you look back farther than stars, farther than galaxies, farther than anything solid at all? You eventually reach a time when the universe was so hot that atoms could not exist. Electrons could not stay bound to nuclei. Matter was a glowing soup of charged particles. And in that soup, Light could not travel freely. Photons were constantly scattered, absorbed, and re-emitted, bounced around like fog in a dense cloud. The universe was opaque, not dark, bright, blindingly bright, but no light could go far. Then something remarkable happened. As space kept expanding, the universe cooled. Eventually, it reached a temperature where electrons could finally settle down and bind to nuclei. Atoms formed. For the first time, the universe became transparent. Light was released, and it has been traveling ever since. That light is still here. It's all around you, right now. It's called the cosmic microwave background. But don't let the technical name distract you. This is not just radiation. This is the oldest light we can see. A photograph of the universe when it was less than 400,000 years old, long before stars, long before galaxies, long before planets. This light fills the entire sky, not coming from one direction, from all directions, which means something extraordinary. No matter where you are in the universe, you see the same afterglow. Think about what that implies. There is no privileged observer, no special location. The universe does not have a backstage. Everywhere is the stage. And this ancient light is the same everywhere to astonishing precision. The temperature varies by only a few parts in 100,000. That uniformity is not obvious. It's a mystery, because a universe this large should not have had time to even itself out. And yet, embedded in that near-perfect smoothness are tiny imperfections, minuscule variation in temperature, barely there. But those tiny fluctuations are everything. They are the seeds of all structure. Slightly denser regions pulled in more matter. Gravity amplified the differences. Over billions of years, those tiny ripples became galaxies, stars, and eventually you. The cosmic microwave background is not just a baby picture. It's a blueprint. Now pause for a moment and let this sink in. The atoms in your body were shaped by patterns written into the universe when it was incredibly young. Your existence is connected to fluctuations smaller than a millionth of a degree in the early cosmos. This is not poetic language. This is physics. But the story gets stranger. Because the early universe was not just hot, it was unusually ordered, smooth, uniform, low in entropy. And that is deeply puzzling. The laws of physics say that disorder tends to increase, not decrease. Eggs scramble. They don't unscramble. Heat flows from hot to cold. Never the other way around. Time has a direction because entropy increases. So why did the universe begin in such a special state? Why wasn't it maximally chaotic from the start? This question cuts deep. It's not about galaxies. It's about time itself. Why the past is different from the future. Why memory works one way. Why cause precedes effect. The arrow of time points away from the early universe, which means something about those early conditions set the direction of everything that followed. When physicists push their equations back toward that early state, they encounter a problem. Densities grow without bound. Temperaturas diverge. Curvature becomes infinite. The math breaks. This is what's called a singularity. But a singularity is not a thing. It's a warning. It tells us we are using the wrong tools. General relativity works beautifully on large scales. Quantum mechanics works beautifully on small scales. But near the beginning, both are needed. And we don't yet know how to combine them. So the Big Bang marks not the birth of everything, but the edge of our understanding. Beyond it, new physics must take over. And that opens the door to ideas that challenge our deepest intuitions. At the microscopic level, the fundamental laws of physics don't care about direction. If you filmed two atoms colliding and played the film backward, the motion would still obey the same equations. Nothing in the basic rules says which way time should point. And yet, the universe clearly has a preferred direction. From order to disorder, from structure to decay, from past to future. That direction is called the arrow of time, and it is defined by a single quantity, entropy. Entropy is often described as disorder, but that's only half the story. A better way to think about entropy is possibility. How many ways can a system be arranged without changing how it looks on the outside? A neatly stacked deck of cards has low entropy. There are very few arrangements that look exactly like that. A shuffled deck has high entropy. There are countless ways to look random. Systems evolve from fewer possibilities to more possibilities, from unlikely to likely. That's what the second law of thermodynamics says. And it has never been violated. Now here's the problem. The early universe had extremely low entropy. It was hot, yes, dense, yes, but it was also astonishingly smooth, uniform, organized. From a thermodynamic perspective, that is an incredibly special state. In fact, it's one of the most special states imaginable. And that raises a disturbing question. Why did the universe start that way? Because if the laws of physics are time-symmetric, there's nothing in them that demands a low entropy beginning. Most possible universes would start messy, chaotic, maximally disordered. Ours didn't. It began in a condition that allowed stars to form, galaxies to condense, and complexity to grow. Everything you care about, life, memory, meaning, depends on that initial order. So the arrow of time is not an accident. It is a fossil, a trace left behind by the universe's earliest moments. When physicists push their equations back toward the Big Bang, this is where they hit the wall. The equations don't explain why entropy was low. They simply assume it, which means something important. The Big Bang model describes how the universe evolved. It does not explain why it began in such a special condition, and that's a clue. In physics, when an explanation works perfectly but requires extremely precise initial conditions, it usually means you're missing a deeper mechanism, and that's exactly what happened here. To explain the universe's early order, physicists proposed a radical idea, one that completely changed how we think about the first moments of cosmic history. It's called cosmic inflation. Inflation proposes that very early on, long before the universe was transparent, long before atoms could exist, space underwent a brief but violent transformation. Not an explosion of matter, an expansion of space itself, exponential expansion. In an unimaginably tiny fraction of a second, the universe grew by an enormous factor. This expansion stretched space so rapidly that any initial irregularities were smoothed out, like wrinkles pulled flat by a sudden tug. Inflation explains several puzzles at once. Why the universe looks nearly the same in all directions, why regions far apart have similar temperatures, why the early universe had such low entropy in the first place. But it does something even more remarkable. It turns quantum noise into cosmic structure. At the smallest scales, quantum mechanics says nothing is perfectly still. Fields fluctuate, energy jitters. During inflation, those tiny quantum fluctuations were stretched to enormous sizes, frozen into the fabric of space. They became the seeds that gravity later amplified into galaxies, which means the large-scale structure of the universe may be the magnified imprint of quantum events. The biggest things we know may come from the smallest. But inflation, for all its success, does not answer everything. It explains how the universe became the way it is, not why inflation happened at all. It pushes the mystery further back, which brings us back to the original question. Was there a beginning? Or is beginning the wrong word? Some theories suggest the universe went through a bounce. A previous phase collapsed, then rebounded into expansion. Others suggest time itself loses meaning near the earliest moments. No before, no after, just a smooth geometry where time behaves more like space, like asking what's north of the North Pole. Not forbidden, just undefined. These ideas are speculative, but they are not arbitrary. They are guided by mathematics, by consistency, and by evidence we can already see. They arise because the Big Bang, as successful as it is not the final word. It is a chapter, not the book. So let's step back. All of this, the expansion, the light, the entropy, the inflation, it can start to feel abstract, vast, distant, almost irrelevant to a human life. But that feeling is an illusion, because this story does not end out there. It ends here, with you. Look at your hands. Every atom in your body was forged in a universe that began hot and dense. Hydrogen, the simplest atom, formed when the universe was minutes old. Carbon, oxygen, iron, the atoms that make blood red and bones strong, were cooked inside stars, stars that lived and died long before the Earth existed. When those stars exploded, they scattered their atoms into space. New stars formed. New planets condensed. Eventually, one small world found itself orbiting an ordinary star. And on that world, the universe learned how to look back at itself. This is not metaphor. This is literal. You are made of matter that has been evolving for 13.8 billion years. The atoms in your body have been part of cosmic expansion, stellar collapse, and chemical complexity. You did not arrive late to the universe. You emerged from it. And now think back to where we started, the Big Bang. Not an explosion in space, not a moment when everything popped into existence, but a transition, a boundary, the moment beyond which our current theories fall silent. The Big Bang was not the beginning of everything. It was the moment the universe became visible. That distinction matters because it changes the kind of question we ask. Instead of asking what happened before the Big Bang, we ask, what conditions made the Big Bang inevitable? What kind of universe allows time to have a direction? What kind of laws allow complexity to grow? What kind of reality gives rise to observers who can wonder about it? Science does not promise final answers. What it gives us is something better, a way to ask better questions. Every time we push deeper, past galaxies, past atoms, past space-time itself, we find not certainty, but structure, patterns, clues. The cosmic microwave background is not just radiation. It's a message, a whisper from a time when the universe was young and simple. And yet, hidden in that simplicity was everything that would come later. Stars, planets, life, thought, and here's the final twist. The universe does not need to know where it came from in order to produce meaning. Meaning arises locally, in systems that can remember, compare, and ask why. Systems like you. The universe is not a machine that broke into consciousness by accident. It is a process that naturally gives rise to complexity. And complexity, given enough time, wonders about its own origins. That wondering is not separate from the universe's history. It is part of it. So when you ask whether the Big Bang was the beginning, you are not standing outside the story, judging it. You are a chapter within it, written by physics, read by consciousness. The universe did not begin so that you could exist. But because it began the way it did, you can ask the question at all. And that may be the most remarkable fact of all. Not that the universe had a beginning, but that after billions of years of expansion and change, it produced something that can look back and say, I am here, and I want to understand.